Okay, today we're going to do one chapter in one day. It's a super big chapter, it's important, but not nearly like chapter 2, which we actually spent 4 days on. So this is the chapter on water. We've already done quite a bit of this chapter. As a matter of fact, I'm going to pull up my handy model, which you guys have seen. So I want you to remember that this is oxygen, then these are hydrogens. These are electron pairs. Of course, there's an electron pair shared here between the two. Now remember all the good stuff that we did with water already. This is a molecule that has two polar covalent bonds. So that means that the electrons that are in between oxygen and hydrogen in this bond are spending more time here than way out here. Same thing for this one. This makes the whole molecule polar. And what we do is we identify this part of the molecule with the hydrogens as being more positive because there's a partial positive charge here, a partial positive charge here, and then we have partial negative charges on these sides. So the way that this molecule behaves, if you remember what we did in class, if this was a negative charged surface, boom. If this was a positive charged surface, boom. So you have to remember that water is going to behave relevant to other substances that are polar. It's also going to certainly behave relevant to other water molecules. Remember we did the grab-ass kind of thing. That's a very important demonstration of what water does with that little demonstration that we had in class. So I'm putting this back. Remember, of course, I guess I should say before I do it, tetrahedral. So it's made up of it's four shapes, tetra, 4 triangles all stuck together. So this is awesome. Putting it back, it's time to carefully present the properties of water. I'm going to put these in a little bit different order than they are in the text. They're all covered in the text and they're all important, and you're going to memorize a lot of good stuff. So what I want to do is put these one at a time. So these are the properties of water. So I'm going to put chapter 3 here, properties of H2O. I'll use the structural formula. So the first one of these properties of water that we need to study is going to be that water is cohesive. So I will say so cohesive is a term. It's important. What cohesion is, cohesive or cohesion, this refers to water molecules being attracted to each other. They are attractive to each other. And I've drawn this before. It's all about partial positive and partial negative. So remember when we draw a water molecule, we always draw the water molecule kind of in this bent form because that reflects the tetrahedral structure. So what we would do is assign partial positive charges to the hydrogens, partial negative charges to the oxygens. And remember we make a pair, opposites, partial positive, partial negative across each polar covalent bond. So that's what we've done. But I wanted to show you what other water molecules would do here. So we had, for instance, maybe one that's like this. And I'll go ahead and stick its charges there as well. Partial positive, partial positive, partial negative, partial negative. And I'll take out blue, and I'm going to show a dashed line here. You would recognize this dashed line as a hydrogen bond. And of course, the nature of this attraction is due to opposite partial charges. Maybe I should write that out. Opposite partial charges. Water is all about partial charges. Every point of the molecule has a partial charge associated with it. That's why water loves itself so much. That's why it is so cohesive. It stays together. Water molecules don't like to leave liquid water. And water evaporates very slowly because of it. So that's the property of cohesion. And I wanted to say that the net of this whole thing, the key to its cohesion, to its super high cohesion, is kind of a maximum level of hydrogen bonding, which I'm going to abbreviate H bonding. A maximum level of H bonding is the reason for these water molecules to be super, super sticky with each other. So that's cohesion. And one thing that's pretty impressive about this cohesive property is that water remains a liquid over a tremendously broad range of temperatures. In the metric system, freezing point is 0 degrees Celsius. Boiling point is 100. But that's a pretty amazing range of temperatures. And it does a lot of good for us on the planet here. You know, if we were to freeze a lot sooner and become a solid, that could cause troubles for us. If we were to, if our solvent of life was to boil too soon, that could cause a lot of problems. Water is amazing. It's fluid over a broad range of temperatures. So the next one that we're going to go into, that's the first property. The second property of water is that it is adhesive. So I should say water is adhesive. And cohesion is within the same. It's attracted to itself. Adhesion is that it's attracted to other polar substances. First thing I want to say about polar substances, if it's polar, it's going to have a lot of polar covalent bonds and a lot of partial charges. So one of the keys to ID polar substances, you look for partial charges, and the more partial charges a substance has, the more polar that it is. So water's attracted to these things. Here's an example that they give in the textbook of water's adhesive properties. There's something called capillary action. Capillary action refers to a capillary, which is a thin straw. And in this case, we're going to talk about a capillary that's made of glass. And one thing about glass is that it is highly polar. A polar substance. So we know that glass, which is made of one material, and water, another, that are both polar should be attracted to each other. That's the property we're demonstrating here, which is adhesion. If you take a beaker, this is the first beaker of many to come. We're going to draw a lot of beakers. So if we take a beaker of water like this, and so here's our H2O, and we drop into that a very tiny little straw called a capillary. What the water is going to do is it's going to fill the straw, but it's going to fill the straw a good bit up. It's not going to go all the way to the top, but you're actually going to end up, if I could do a blow up of this area here, so here's a section of the straw in blow up, a section of the straw, the water looks like this in the straw. I guess I'll say that this is a blow up. So what's happened, you can even see here, the structure is called the meniscus. right here. But what's happening is that the water likes the opposite charge, the polar charges, the polarity of the glass so much that it binds to and kind of creeps up the side. You can see that happening right here. That's an example of adhesion. So materials that are different but polar, but different types of materials that are adhering together. You can think of the word adhesive. It's the same thing. Adhesives are used, well, sometimes to glue like things, but also different things. So adhesion is a very important property of water. Number 3. Okay. So the third property of water is that it has a high. So water has a high specific heat. We're going to define the specific heat as how rapidly molecules move. So this thing here is kind of a measure of how rapidly molecules move. Hydrogen bonding is going to resist that movement. So substances that are nonpolar, that don't have hydrogen bonds holding them together, move a lot more erratically and a lot more than their polar counterparts like water. And when particles move, it's crazy. And every once in a while, one of them's booted out of the system. And of course, that's the process of evaporation. I'm going to go into something in a minute about this. But right now, let's focus here. So water has a high specific heat, and that's what this measure is. It takes a lot of temperature to get these molecules to really move about relative to one another. Here's the essence of it. Water is, compared to other substances, water is slower to heat, and water is slower to cool. So those are two great properties that's kind of under this category. All of this is due to H bonding. All right, so that's that. All right. Number 4. Water has a high heat of vaporization. A high heat of vaporization, and this is defined as the amount of energy that is required to convert 1 gram of liquid water to gas. So of course, that's where the word vapor comes in. Vapor. So the amount of energy required to convert 1 gram, that's a number 1 right there, not large. So 1 gram of liquid water to gas. And it takes a lot. I want to show you something. Compared to other substances, water is kind of the king. And we can do an experiment that you'll pretty much get. So I want to demonstrate, here's an experiment with beakers. So I'll abbreviate the word experiment. What we're going to do is we're going to take a beaker of water. So that's H2O. We're going to take a beaker of the same size, and in that beaker, let us stick ethanol. How about this? So C2H5OH. You guys remember this one? We played with it a lot. So that is ethyl alcohol, and that's water. And we're also going to take a beaker that we set up with the same amount of another substance. Let's get a good pen here. Equal amount of let's put butane in there. C4H10. So these are our big molecules. Lighter fluid, ethanol, and H2O. Here's the condition of the beakers right here at this represents time equals 0. This is the start of the experiment. And then down here, time, let's just put a good bit later. Hours later. So time equals hours later, and let's draw the same beakers and see what we expect after that time has elapsed. So I'll draw my beakers. Okay, so there's the same beakers. So what we would expect to happen in this particular case, we're going to have some evaporation. So maybe the original line was here, and maybe the current water line several hours later, especially in this arid Denver climate, is a little bit lower. So there's H2O. Now the next question, however, is what's going to happen to this ethyl alcohol? Is it going to evaporate more or less than water? Well, remember that what's holding these water molecules together is hydrogen bonding and partial charges. And remember that water's all about partial charges. Both of the hydrogens have partial positives, and then the oxygen has a couple of partial negatives. It's just nothing but grab. And then this ethanol over here, yeah, it has polar covalent bonds on one end of the molecule. It has partial negatives on its oxygen, and then a partial positive on that one hydrogen that's stuck to the oxygen, and then of course a partial positive on the carbon that's stuck to the oxygen. But the rest of the molecule, totally nonpolar. So I'm going to tell you, you may have predicted this, ethanol is going to evaporate a lot more in this time period than water because ethanol has a lower heat of vaporization. It more easily vaporizes is the idea. The last one is very interesting. If we wait, for several hours, butane is pretty doggone volatile. It's gone. There might be a trace. There might be a trace of residue in the bottom. There is not a single polar covalent bond in butane. Therefore, there's not a single partial charge. There's not a partial negative or a partial positive. There's no relationships between butane molecules in the category of partial charge attraction. No hydrogen bonding. Butane evaporates rapidly. And you guys, a similar molecule to butane has even more carbons, and it's called octane. And you put that into your gas pumps, and you guys can see that stuff vaporizing on a good day right when you're pumping it in. And you see those convection waves that are coming out of the gas. So there's just nothing that holds those molecules together. They vaporize very quickly. So that's the concept here. The more H bonding, the more they stick together, the harder it is for them to actually leave, and leaving is called vaporization. Excellent. One little add-on to this experiment is that if we did the same experiment but added heat to the process, everything would happen and water would still be the last to vaporize. It would be slower, but it would happen a lot more quickly if we added temperature to the whole mixture. So that's kind of cool. So there's a little bit of beaker chemistry that you can just kind of see on the board. Pretty neat. All right. So there's 4 big properties of water in a great beaker experiment. We've got more to do. So 1, 2, 3, and 4, all about hydrogen bonding, without a doubt. And water's special. And we're going to do some other ones that get a little more complicated. The next one actually is a property of water that's extremely important ecologically, so to the world around us. So number 5 is that solid water. So what do we call solid water? You're thinking about it, aka ice. Solid water is less dense than liquid water. So what we're going to have to do now is define a very important term. I might stick some color on this thing. So this guy right here is a concept of density. Very important term for chemistry. And what density is a measure. Sorry about this, I got to cap some pins. So density is a measure of how much of a substance, so the weight of a substance per unit volume. So you might think of some really, really incredibly dense substances. I don't know if any of you ever in your experience have seen mercury, which is this bizarre shimmering metal. If you've ever, I remember seeing mercury is incredibly dense, tremendous density. And I remember seeing a chemistry professor's collection of mercury that came from broken thermometers for decades of his teaching. So somebody would break a thermometer in the lab, they'd collect the mercury, put it in this beaker. And this was a large beaker, and it was about 1/3 full of mercury. And that thing was like a 2-hand struggle to lift. It's really, really heavy. So not everything is of equal density, because if I had the same sized beaker as this mercury beaker and had it 1/3 full of water, I mean, it's completely different. I mean, pick that up super easy, one hand, no problem, you know? So density is a concept of weight per volume. And what we're going to talk about in this property is that solid water is less dense than liquid water. In fact, the peak density, water exhibits its highest density at 4 degrees Celsius. So I want you to think about this for a minute. If we had a freezing, chilling phenomenon, it happens in Colorado every winter, especially up in the mountains. So it's getting colder and colder and colder and colder. It's chilling the lake. And at some point, the temperature is going to get below that 0-degree freezing point. And ice is going to form when it gets to 0 degrees. And when ice forms, it's going to float above the either warmer or colder water below. So let's do a little kind of picture of Rocky Mountains. I should make them a little bit more steep. So here's kind of a little valley between the Rocky Mountains, and we have a lake there. So this is our Rocky Mountain Lake, and we'll say that this thing is below timberline, so I'll make some pine trees here. So here's some trees, some good trees kind of taken off. Beautiful Rocky Mountains, right? So we're looking kind of at a cutaway view of the lake, and what's going to happen when everything becomes snow. Of course, I don't have a white marker because that wouldn't work. But let's suppose that the red is snowfall and everything gets cold, and so we have this layer of ice that's floating on the top, and everything else is cool. Underneath, the ecological significance here is that this water below, probably the water at the very bottom of the pond is 4 degrees C, and the ice itself is going to be 0 degrees C, and it floats. So let's write that in big letters. It floats. Because liquid water is more dense underneath, is what I'm saying. Now, what does that enable to happen? Some of you are doing this. You're ice fishermen. You walk out, bore a hole through the ice, and you're catching fish that are swimming around down here I'm drawing fish. So they might not be the greatest fish to you, but our little lake has fish in it, and they can exist in their liquid environment, not frozen solid, because that's not how it works. Once ice forms, it comes and floats to the top, colder water below. The other great thing about it is the insulating properties of water in its solid state. I mean, it definitely kind of cuts other things out. So, tremendous ecological significance, and I need to write that on the board. So, big time ecological significance. And I'm abbreviating SIG. So that is the 5th property of water. All right. This one is extremely cool. Water is a great solvent. Gonna have to define that term for polar substances. Okay, so the first thing we need to do is define solvent. A solvent. So what? This is the language of mixtures. Terms associated with mixtures. Mixtures, of course, are things made of more than one kind of substance. So a solvent is the major component. Of a mixture. There's only one solvent in a mixture. Then the other things that are there are called solutes. So these are minor components. I'll put that as, you could have a simple mixture with just one solute and one solvent, but usually you have a lot more than that. So minor components of a mixture. That's what solutes are. So we'll take an example of Coca-Cola. Coca-Cola, I think that's how you spell it. So if you guys, what's the solvent of Coca-Cola? The solvent is H2O, and of course, that's what this whole property is about. Let's start to name some solutes. There's some good solutes here. We have, back in the day, it used to be sucrose. It was regular great sugar. Now, unfortunately, matter of fact, let's do Coca-Cola that we acquired from Mexico. That's a much better Coke. So we import Coke that is bottled in Mexico, and they use real sugar. So and that's what they say. They call it sugar. We're going to get into that later on, but that's one of the solutes. I think we have that caramel coloring, that makes it brown. I think that we also have in there, I don't know if they add caffeine to the mix, but Coke is, it gets you up. So caffeine would be one of the solutes. And then one more solute that I'm thinking about right off is called phosphoric acid. So there's 4 of the solutes that are in a Coke. Coke is a mixture, and the solvent is water. One thing that I should tell you then is that all of these ingredients then should have some polar properties to be able to mix with water. If they didn't have a polar property, or some degree of what they call solubility in water, then you'd have layers. And I want you to think forward about that. Think of things that don't mix, such as maybe salad dressing. You've got vinegar and water and some other stuff in one layer. I'm thinking of like a vinaigrette. And then you have olive oil, right? And you let that thing sit in the counter just for a little while after you've maybe shaken it up and used it on your salad, and you have 2 layers. So future thinking is that top layer is much less dense than the lower layer, and in this case, the top layer is made up of non-polar stuff that we call fat, and that's in our future to really sink our teeth into what fats are. Back to this. So this is Coca-Cola, good Coca-Cola from south of the border, and the solvent H2O, polar, sugar's definitely polar, and on down the line. So that is the 6th property. And finally, not actually finally, we've got 2 more. The last one's especially big. Okay. So our next property of water, number 7, is very cool as well. Water organizes non-polar substances. So I want to do something really cool. I'm going to intimidate you with a sizable molecule. We're going to draw a pretty good sized molecule here. Let's do this. This is a molecule where I'm going to make what's called a hydrocarbon chain. That's right around the corner for us. So I'm going to stick a bunch of carbons together like this, and then I'm going to stick some hydrogens. I will never ask you to draw this particular molecule. You should copy it in your notes because you can interpret the molecule. So we're following our rules. Remember that our hydrogens are always flags, and that carbon forms 4 covalent bonds and hydrogen forms 1. So that's good stuff. That's good stuff. And then at this last one here, I'm going to draw something really funky. A double bond O and an O and an H. So as we've done in the past, we are going to identify all of these bonds here as polar covalent bonds. If you wanted, you could stick a partial positive, a partial negative, a partial negative, partial positive, and then a partial positive, partial negative. There's a lot of partial charges on one end of the molecule. But look at this wicked thing. This hates water. There's no basis for water to be attracted to this part of the molecule going this way. We've got a lot of basis for attraction here. So I'm going to show you the experiment. What we're going to do is we're going to take some of this stuff right here, and we're going to squirt it. This is a fluid. We're going to, by the way, I'm going to tell you what this is. This is a fatty, a fatty acid. I think fatty is like a marijuana cigarette, legal in the state of Colorado. A fatty acid. So this is a molecule that has fat-like properties, which essentially means non-polar over here. And then you have all of this polarity here. And when you pour this stuff into a beaker of water, I'm going to have to draw a big beaker, so I want you to as well. A big beaker of water. Here's our H2O. So water's in here. When we send those in, I'm going to do something right now to make this easy. This molecule, too big to draw, we're going to make a cartoon of it. And we're going to see a lot of this in the future. The cartoon of the fatty acid. The cartoon of the fatty acid is going to be a stick and a ball. The stick is what we're going to call the nonpolar tail. The nonpolar, aka fatty tail. And then this part right here is what we're going to call the polar head. So what happens if we pour molecules with nonpolar tails and polar heads into a polar substance like water? They can't totally mix in because this is too much hatred for water. Nonpolar hates water. Polar loves water. So here's what's going to happen to these molecules. Maybe we should make them colored so they kind of they stand out a little bit. I'm going to change this so it stands out to this brown color. So here's what happens. All these molecules are going to dive into the water, and water will organize them as a monolayer on the top with their tails shooting straight up. So we've poured this stuff into the water, and it accumulates on the surface in a very directional way. Head down, tail up, because tail hates water and head loves water. That is the process of organizing these nonpolar tails. That's the nature of this particular property of water. Extremely cool. So now we're sitting with 7 incredible properties of water, and we got one more big one to kind of sink our teeth into. All right. Okie doke. So the last one is fun. Number 8. Water does something incredibly cool. It dissociates. Dissociates means that it breaks down. It's a chemical reaction. This, of course, goes with that last little lecture. H2O is the reactant, will go to become H plus ion. Do you remember when we talked about H plus being kind of that weird rule breaker? I mean, H, hydrogen, the element, that can ionize, as I mentioned, and it can also form one covalent bond. Well, here's your first example of it ionizing. And they call that process dissociation. It also forms a molecule itself, a hydrogen stuck to an oxygen that itself is an ion. We need something new to describe this. Because there's a covalent bond between these two, this is a molecular ion. So it's a molecule that has an unequal number of electrons and protons. So this is a molecular anion, right? Good stuff. And this, of course, is just a regular cation. And this is dissociation. The other thing about it that ties in with our last little lecture on chemical reactions is that this is reversible. So here's what you should be thinking about. If you think about water at the molecular level, there are intact water molecules, and every once in a while, one of them will dissociate and break into a hydrogen ion and a hydroxide. That's what they call it, or an OH minus ion. So this one is called a hydroxide ion. So OH minus, I'll put that here, OH minus is called a hydroxide ion. All right, my camera's blinking, so I'm gonna take a little look at to see what's going on, and I'll be right back. Okay, back. Sorry about that. I filled up a disk. So now we're back to business. And what we're going to do, this is where it gets intense. So we've described that water molecules dissociate. That's the name of this reaction. And form hydrogen ions and hydroxide ions. Now, remember the other thing about chemical reactions from the little lecture that we had before this one was that there's an equilibrium. Not too many of these molecules do this at any given time. I mean, a very tiny amount. So the net equilibrium of both of these reactions occurring is to keep about 1 in a million molecules will be in this state, where they've broken apart, where they've dissociated. It's pretty tiny. So I guess what I'm trying to say is just imagine that everybody living in the greater Denver metropolitan area was a water molecule. At any given time, one of all of those people living here now would explode into 2 parts, maybe their head and the rest. So the hydrogen ion and the hydroxide ion. So only one of all of those people living. That's about representative of how many water molecules are doing this. But I have to tell you that the chemical consequences of water dissociating is tremendous. And what we're going to see is sometimes other substances can mess things up by putting out their own H plus into the mix. And as soon as you get a lot more of that than natural water, you have acid. Or another substance might put a lot of this in. And when you have too much of that and it gets out of balance, you're basic. So acid and base is the topic of the time, and it has to deal with this concept of dissociation. Now I'm going to throw some really, really heavy chemistry at you right now to kind of get a concept of what these numbers are. What I want to do is tell you, first off, I need to kind of I'm going to put it in a box over here. I'm going to get kind of like an insert, a plug-in, if you will. And this plug-in has to do in chemistry with the concept of mole. So a mole of substance is equal to 6.02 times 10 to the 23rd. That's a massive number. 6 times 02 times 10 to the 23rd particles. So a mole of water would be 6.02 times 10 to the 23rd molecules of water. I guess I'll just say items of a substance. I'm messing that up pretty bad. That'll be okay though. So this is what a mole is, and what I want to tell you is that the weight in grams of a substance is equal to its atomic mass. Here's what I want to do. I'm going to put this into perspective. Suppose, for example, that we have the molecule CH4. You remember this one? So it's carbon, single bonds with 4 hydrogens. We know their atomic masses. Carbon's atomic mass is about 6, and hydrogen's atomic mass is about 1. So CH4 would be equal to carbon is 12. I hope I can erase that, but if I can't erase that, carbon is 12. Remember, atomic number 6, but 12 protons and 12 neutrons. Hydrogen is 1, so 12 plus 1 plus 1 plus 1, let's see, plus 1. 12, 1, 1, 1, 1 is equal to 16. And what I want to say to tie all this together is that 1 mole of CH4 would be equal to 16 grams. So that's what we're talking about when we get into that concept of that molecular weight. We had atomic weights, which is what we've added up here approximately. So we'll make this about 16 grams. That's how this whole concept works. Now, I don't even know if this is very important to you, but it gives some sense to this molecule and how very, very small that molecules are. And what we're going to use this for is to kind of try to understand what this means. So here's the deal. I'm going to go ahead and erase this stuff and keep my equation up. And what I'm going to do from here is tell you that the concentration of H+, so we have to identify concentration. It's a new term, another chemical term, kind of like density was. Concentration is the number of particles of a substance in a mixture. So what we're going to use for concentration is called molar concentration. Molar concentration will be defined as the number of moles of a substance per liter. And I'll go ahead and write liter out. Number of moles per liter. In pure water, the purest water that we can get, in pure H2O, the molar concentration of H+, the molar concentration of H+ is equal to 10 to the minus 7th moles per liter. I have one other thing to do to these notes. Writing the word concentration is pretty crazy. So in the future, I can also use a shorthand. A shorthand for concentration is using brackets around the substance. So I put H+ in brackets. This is universal. You're going to see this in your chemistry courses. If I put H+ in brackets, that means concentration. So I could say in shorthand here, therefore, that H+ concentration in pure water is equal to 10 to the minus 7th moles per liter. Now, everything that I've said so far about this is you've got to be on top of this. This is dissociation. And you have to know that there's very, very few of these water molecules doing this at any given time. And this number shows that. 10 to the minus 7th moles per liter is a pretty tiny amount. That's what I want you guys to kind of stick to. So the next thing we're going to do is going to get a lot easier if you're just capable of memorizing it. So, without paying any attention to the big math, I'm going to go up here now and tell you that what we've done in science is that we've created a pH scale. And pH stands for parts hydrogen. And what we define it as is going to be, we've created this concept of pH. We're going to define pH as equal to minus the log of the concentration of H+. That's huge. Now, just to let you know, in pure water, this equation becomes, the pH of pure water becomes minus the log of 10 to the minus 7th moles per liter, right? 10 to the minus 7th moles per liter. And what this transformation does, this logarithm transformation, if you plug this even into your calculators, if you put 10 to the minus 7th and take minus log of it on your scientific calculators, and I recommend that you do that, here's what you're going to get. You're going to get the number 7. So the big, huge, super huge take home about this is that in pure water, the pH of pure water is 7. Now, the bigger point is here's what it means. So remember the equation. H2O going to, or coming from, H plus OH minus. A super, super important thing here is that because this is all that's there in pure water. That's it. That's all you have in pure water. There's nothing else there. Because of that, at any time in pure water, H2O, the concentration of H plus will equal the concentration of OH minus. Because that's all you've got. You've got water molecules breaking apart. There's no way to have any imbalance between this and this. That's the total story. So in pure water, I get one more color to make this as festive as I can. In pure water, the pH is 7, and the concentration of that is of H plus and OH minus is equal. Remember that pH is about the concentration of H plus. That's what it is. Parts hydrogen. That's what the H stands for. And we've done a transformation based on all this molar stuff to come up with the number 7. So the simple story is that when OH minus and H plus are equal in a solution, and there's that much of it, pure water dissociation, we call it pH 7. pH 7 is a solution that we also call neutral. So we call pH 7 also called a neutral solution. 3 exclamation points there. I know that this is probably the most intense part of this lecture, and we'll try to get some good work on mastering to kind of help you understand it. But I think if you guys walk away from this and you know that pH 7 is neutral and what that means that we have 10 to the minus 7th moles per liter concentration of H plus, and the concentration of H plus is equal to the concentration of OH minus. Boom, boom, you're good. This is the big part right here. Tattoo that in your brain. All right. So, after doing all of that intense stuff, what we get to do is define, then, therefore, a couple of things. So, when H plus concentration is not equal to OH minus concentration, we've got different stuff. That's when we get into acid and base. Acid and base. Acid would be those solutions, I'll put this arrow like that. This is when H plus concentration is greater than OH minus concentration. Base is when OH minus concentration is greater than H plus concentration. When we do the pH of this, this is pH values less than 7. And then these values would be pH values greater than 7. So there's some breakdown for differences between acid and base. We'll go on to define acids as substances that increase, that donate H plus to a system. So substances that contribute H plus to a system. Bases we will call substances that contribute OH minus to the system. Okay? Oh my God, this is great. Incredible. So, what we're going to do now is celebrate the pH scale as it shows up in your book. So, on page 54, there's figure 3.10. So what we're going to do with that is I'm going to show you kind of the pH scale. Your figure starts with pH values under here of 0, 1, 2, 3, 4, 5, 6. I'm going to draw this old neutral in 7, and then 8, 9, 10, 11, 12, 13, 14. That's as far as your scale goes. And they've actually shown some things. So the pH 7 is what we've called neutral. And then if you would do the math on this, this is 10 times more concentrated, 10 times more H plus than this, 100 times more than this, 1,000 times more than this, 10,000 more times than this. So this is a magnitude of 10 every step up. So times 10 more, 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 etc. on up. Same thing down here. Is for H plus 1/10, 1/100th, 1/1000th, but for OH minus it's of course more. So anyway, some things that are worth mentioning is we can think about some substances. What you've all tasted acid, you taste it every day, and I'm talking about like citrus. So sour candies, fruit flavored candies have citric acid in it. The sodas. Just regular citrus, orange juice, grapefruits, lemons, very, very acidic. And those things occur up here, but there's kind of this kind of sour taste. And of course, maybe I should say that sour occurs here. If it ended up in your mouth here, it'd burn the crap out of you. I mean, like damaging, like injury, serious injury. You don't want that kind of acid in your mouth. But that's a kind of a concept. So some of the pH considerations that we have from the book. Lemon juice is way up here. Lemon juice is way up here. That's incredibly acidic. I'll pick another one out that's kind of neat. Not that you've ever set out to drink urine, but if you did, you would find urine to be slightly sour, and pretty much it's very mildly acidic. On the other side, let's pick out a couple of bases from the table. They don't have any good ones there. Seawater, pH 8. I mean, yeah, you've all tasted that, but of course salty, but seawater is pH 8. I'll pick one more out of the table that's pretty strong. Interestingly enough, way down here is the world of oven cleaner. And if you've ever cleaned an oven with that stuff, that's really intense. The further away you get from neutral, the more disruptive impact that these solutions could have if they came into contact with you. Because your body is pretty much teetering around neutrality. The pH of blood that's in your table there is about 7. So we kind of operate right here, and the further that we get away, it gets pretty intense. Now, there are some bacterial organisms, some extreme organisms, that actually love acidic places to live. So it's great stuff. So that's the pH scale. Definitely know what the numbers mean, certainly in terms of acid and base. Definitely know what the word acid means, more H plus than OH minus, and what the word base means, more OH minus than H plus. All of this relates to the dissociation of water. And it's our last property of water, and that's where we'll close the book on chapter 3. So it's over, and that is the last lecture for you guys.